When we rub silk on a glass rod, a transfer of charge occurs, which can be experienced by touching the silk. You are rewarded with a mildly discomforting shock. Will rubbing for a longer time deposit more charge on the silk? How much or how little charge can you transfer onto the silk? Let's find out. Electron and proton both have charge of the opposite sign, but of the same magnitude E, called the elementary charge. It is one of the important physical constants. Its value is 1.6 into 10 to the power minus 19 C. We know that charge is developed due to the transfer of electrons. During the transfer, the object receives n electrons, develops a negative charge Q on it, which is n times the charge on an electron. That is, Q is equal to n into minus E, or Q is equal to minus NE. The object which has lost n electrons has a deficit of n electrons, and so a positive charge Q developed on it is n times the charge on a proton. That is, Q is equal to n into plus E, which is equal to Q is equal to plus NE. In general, Q is equal to plus minus NE, where n is a positive integer, which can take the values of 1, 2, 3, and so on. Thus, the magnitude of charge Q developed on an object is not arbitrary, but an integral multiple of the elementary charge E. In other words, the charge is quantized in the unit of elementary charge E. The fact was first suggested by Faraday and established by Millikan's oil drop experiment. The quantization of a charge is important at a microscopic level, where the charges are of the order of a few tens or hundreds of E. Can you guess how many elementary charges are present in 1 coulomb of charge? It is 6.25 into 10 to the power 18. Such a large charge consists of a large number of elementary charges, and the graininess or the structure of the charge does not show up. So for a macro charge, quantization is ignored by considering it to be a continuous distribution of charge and not a discrete one. Charge is additive in nature. Let us rub a neutral silk cloth with a neutral glass rod twice. In the process, the silk cloth acquires 3 electrons. When we rub it 10 more times, the silk cloth acquires, say, 6 additional electrons. The total charge on the silk cloth is now minus 3E plus minus 6E, which is equal to minus 9E. Hence, the charge is additive in nature. Consider a system containing charges 2 coulomb, 3 coulomb, and minus 4 coulomb. The total or net charge of the system is 2 coulomb plus 3 coulomb minus 4 coulomb, which is equal to 1 coulomb. The total charge of a system is the algebraic sum of all the individual charges. Charge is conserved. Before rubbing, the total net charge on a neutral glass rod and the neutral silk cloth is 0. After rubbing, the glass rod acquires a positive charge, while the silk acquires an equal amount of negative charge. Hence, the total charge is still 0. Thus, we say that the total charge of an isolated system is always conserved. For example, a radioactive nucleus of uranium has a positive charge of 92E before decay. After decay, the total charge of the thorium nucleus and the helium nucleus is 90E plus 2E, which is equal to 92E, which is the same as that before the decay. Thus, the charge is conserved in every physical process. This implies that charge can neither be created nor destroyed, but can only be transferred from one body to another. To summarize, charge is quantized, charge is additive in nature, charge is conserved. If every material were good at transferring charges, life would have been full of shocks, as our civilization is highly reliant on electricity. There must be some materials that keep you safe from shocks. To find out more about these, stay tuned.